Yay!
Yay! Okay, now let's look at some of the fundamentals of current running through wires. The first example is, let's just take a copper wire. It'll be important that it's copper in just a second. And let's look at what happens if you have a 5 amp current running through a 12 gauge wire. And a 12 gauge wire is about 2 millimeters in diameter, so we'll go with that. That makes it kind of easy because that's a radius of 1 millimeter, so that will be pretty easy to compute the cross-sectional area, which we'll need in just a second. Okay, first of all, if I have this current running through the wire, one thing we might be interested in is, well, it's a flow of what? I mean, it's a flow of charge through the wire, right? So how many electrons per second are running through a particular boundary? Let's say running through that little, if that's a cross-sectional membrane of the wire, how many electrons per second are running through there? Okay, so we know that there's 5 amps of current, and that's 5 coulombs per second. An ampere is a coulomb per second. Okay, well then we're almost home, because that is 5 coulombs per second. Oh, put the second in just a minute. It's 5 coulombs. And then what I also know, each electron is 1.6 times 10 to the minus 19th coulombs per electron. So those divide out, and what I'm left with is just the number of electrons per second, right? So that gives me, if I divide those numbers out, I get like 3.12 times 10 to the minus 19th. Oops, sorry. It's a big number. 10 to the plus 19th electrons per second. Okay. Neat. So going through the wire are, let's see, what is that? 312,000 trillion, 331 million trillion electrons per second. The number doesn't matter. Or naming the number doesn't matter. Anyway, it's a lot of electrons per second running through the wire. That might lead you to believe that the electrons are zipping through the wires, right? In order to have 10 to the 19th of them go by every second. It turns out that's not quite right. And the reason is because electrons are just really, really tiny. Okay, so we can ask the following thing. Let's compute this. What is their speed? And by the way, in the books, you'll see this called drift speed. The reason it's called that, as opposed to just plain old speed, is because these electrons are more or less free inside the metal to roam. And so if you just say speed, what you might be thinking of is just their sort of random thermal motion inside, because the wire is at some temperature, so the atoms, the copper atoms inside, are jiggling back and forth, and they're knocking these electrons around. And so these electrons have some characteristic speed just because they're in a metal that's at some temperature. We're not computing that. We're just computing, because of the electric field that's applied inside the metal, what is their drift speed down the wire? So not their random thermal motion, because if you think about it, really, their thermal motion is going to average out to 0. They're just as likely to be knocked one way as the other. So if you have a whole great many of them all sort of being bumped around, their sort of average motion is 0. So we're talking about just the average motion of these things down the wire. Okay, how are we going to get that? Well, let's go back to the definition of current. Current is defined as some amount of charge. That's not really, this is a different use of the delta, right? It's not like final minus initial. But that just means sort of a flow of charge in some amount of time. Charge per unit time. How how we're going to do it is, if this, let's forget just for a second that the electrons are negatively charged. They're just charges. Just suppose they're positive. If we have a bunch of these electrons in the wire, how much charge is flowing past? What we're going to do is we'll write it down like this. The amount of charge in the numerator is just going to be, let's write it like this. It's the number of electrons. I'll write it like that. Non-standard notation. It's the number of electrons times the charge on each electron, right? Because that'll give us the total amount of charge. And then that'll be divided by time. What is the number of electrons? We'll write it like this. N sub E is what we're going to call the number density of electrons. That's going to be the number of electrons per cubic meter, because that's something that we'll be able to find here in just a second. So the number density, number per cubic meter, times the volume, that'll get me the total number of electrons, right? The density times the volume gets you the total number, times the charge on each electron. That'll be divided by our delta T. All right. Now, what's neat is, what is the volume of this thing? Okay, here's the way we're going to have this set up. Let's suppose in one amount delta T, maybe it's a second or whatever it is. Let's suppose in this little segment of wire that all the electrons in that little segment in the time delta T, all of those electrons run through the boundary A. Let's say that. Then how long is that segment? That segment then is going to be the speed of the electrons times delta T units long. Speed times time gets you distance, right? Way back in physics 1. So that is our length of this little segment where all those electrons, if they're moving at a speed v, all those electrons will go past the boundary. So then I can write the volume. Then the volume is just going to be, it's just going to be the length times the area, right? That sweeps out that sort of cylinder. So that's going to be A times V delta T, and then I still got my E on top. Oh, and I still have my delta T on the bottom. And then look how neat this is. The delta T's go away. So what I have left is current is the number density times A times the speed times the charge on each electron. Okay, that's a neat result. And it's pretty general. Anytime you have the flow of anything, a flow of a gas through a tube or water through a pipe, you're going to end up with the same kind of thing representing sort of a current, right? So this is going to be pretty general. But this is how we're going to get at that V. Let's solve that for V. So this means that V is just going to be the current divided by, what do I have left? N, the number density times the area times E. Okay, well, for this wire, I know the current, I know I. Let's see, A, do I know A? Yeah, I know the cross-sectional area, or I'll be able to compute it pretty easy. E, I know that, the charge on each electron, I got that. So the thing I don't know is that Ne, the number density of electrons. Okay, so let's see if we can be clever and compute that. Okay, let's run over here real quick. Let me separate these two. Number density of electrons. Okay, here's what you need to know. For copper, copper is element number 29. So it's got 29 protons in the nucleus. It's got 29 electrons. Here's the cool thing about copper. 28 of those electrons are fairly strongly held. The one electron that's left way on the outside in an outer shell is only weakly bound. And so that's the one that's more or less free to just roam around the metal. It's another way of saying it is that copper, that the copper atoms are packed close enough together so that that outer electron is just about pulled to the next atom or the next nucleus as it is to its own nucleus. It's pretty close. So it's essentially free. If you bump it, it can kind of jump from atom to atom and flow. So each copper atom, here's the point, each copper atom has one free electron. That's the idea. So if I can get the number of atoms of copper per meter, that's like a number density of copper. If I can get that, then that also has to equal the number density of electrons, free electrons, right? Because there's one electron per atom that's free. Okay, so here's what I'm going to do. There's a couple of constants for copper that I can look up, and then we can play around with the units. Here's one. Copper has a density of about 9,000 kilograms per cubic meter. It's pretty close. Also, I know this. Copper has an atomic weight of about 63.5 grams per mole. That's also 0.0635 kilograms per mole. So maybe you can see what I'm about to do. If I divide those two numbers, look at the units. If I divide those two numbers, I get this. 9,000 kilograms per cubic meter divided by 0.0635 kilograms per mole. Look at this. Kilograms go away, and what I get, if you do this, is about 142,000 moles per cubic meter. Well, now I'm almost home, right? Because if I know how many moles there are, I multiply by Avogadro's number, and then I get the number of atoms. So that equals, if I multiply by, 6 times 10 to the 23rd, I'm going to get about 14 to 6. That's going to be something like 8.5. 10 to the 5th and 23rd is 28th. Atoms per cubic meter. There we go. There's our number density. So for copper, for every cubic meter of copper, apparently there are 8.5 times 10 to the 28th atoms. And what that'll mean then is that there's 8.5 times 10 to the 28th free electrons that are able to flow per meter, per cubic meter. Oh, that's our number density. Okay, so I'm going to take this, plug it right in there. And if I do, then I get a really interesting number. So the drift speed is going to be 5 divided by, okay, there's this number, 8.5 times 10 to the 28th. A is pi times r squared. Pi r squared is the cross-sectional area. What is r? 1 millimeter, right? 10 to the minus 3. So square it, and I get 10 to the minus 6. And then 1.6 times 10 to the minus 19th. If you plug all those numbers in, what you're going to get, what did I get? You get a really interesting number, which is 0.12 millimeters per second. 1.2 times 10 to the minus 4th meters per second. Look how slow that is. That's really neat. So it's not true that, and 5 amp current, that's a pretty healthy current. So it's not true that when you turn on a light switch, the electricity, the electrons from the light switch get to the light immediately, like the speed of light. That's a little surprising for people. Sometimes you think that the electrons move through the wires at about the speed of light. They really don't. They crawl slower than molasses. It takes 10 seconds for them to go a millimeter. Right, so to go a meter, it's going to take 100. Is going to take the better part of a day, right? A little over a day to go a meter. So when you flip on the light switch, you don't have to wait, thank goodness, for those particular electrons close to the light switch to make it to the light. Instead, it's sort of like having the pump already primed. All along the wire, there are already electrons ready to march. And So you don't have to wait for those particular electrons to get to the light. The ones that are already near the light are already starting to move. So something is propagating through the wire near the speed of light, but it's not the electrons themselves. What it must be then is their marching orders. It's the electric field. The electric field is what propagates through the wire at close to the speed of light, or at the speed of light. So it's the orders to march, and then they all start marching in unison, very, very slowly. But that's where the speed of the current comes from. So it's kind of neat. That usually surprises people, that the speed of electrons and wires, the drift speed of electrons and wires, is so slow. We'll show in the future the thermal motion. What's the actual speed of the electrons of a particular electron in the wire? It turns out it's on the order of like 100,000 up to 1,000,000 meters per second. So they bounce around like crazy and just have this tiny little component down the wire, 1/10 of a millimeter per second. Oh, also notice what happens if the wire is a little bit thinner. If the wire is a little bit thinner, that affects the cross-sectional area, right? The cross-sectional area will go down as the diameter of the wire squared. The area is going to go down. And that means the velocity goes up. So as the radius of the wire gets smaller, as the wire gets skinnier, the speed of the electrons, the speed of the current gets bigger. And this is why if you have a really, really skinny wire, like a light bulb filament, this is why they heat up and glow like old-fashioned incandescent lights, because you're trying to jam this current through a really, really skinny wire. Look at the filament, it's really, really thin. So you're trying to jam the current through a little thin wire, and it has to go really, really fast, and there's lots of collisions between the electrons and the atoms in the wire, and that heats it up and makes it glow. Okay, next time we'll actually deal with the resistance of a wire, see how we can calculate that.